Hi everyone, let's take a look at problem 3, which says a uniform horizontal beam is 21.7 feet long and weighs 1,060 pounds. Well, that's a lot more realistic. It is supported at either end. A vertical load of 14,830 pounds is applied to the beam 9.071 feet from the left end. Find the reaction at each end of the beam. Okay, so the first thing I do is draw the picture. So we have this horizontal beam, and it's 21.7 feet long and weighs 1,060 pounds. So I just put that information over here on the right side. Okay, it's supported at either end, and then a vertical load of 14,830 pounds is applied 9.071 feet from the left end. Okay, so there's my picture. Well, we can go through the lefts are equal to the rights. We don't have any left or right forces working on this beam, so we can skip that. And honestly, I don't think there's one problem here where we use the lefts are equal to the rights. Okay, so on to the ups are equal to the downs. Well, we have two forces acting in the upward direction, but we have variables for both of those. So that equation is not going to help us, at least not right now. So let's go on to the clockwise is equal to the counterclockwise. So we can hold our beam stable at any point along the beam. The three logical places are at the left end, the middle, and the right end. Since we have the length of the beam is 21.7 feet long, I would choose either the left end or the right end. But then we know that this weight, this 14,830 pound weight, is 9.071 feet from the left end. So I would choose the left end. Okay, so, if we go clockwise is equal to counterclockwise. So if we're holding this beam stable right here, what's forcing it to go clockwise is this 14,830 pound weight. So we have 14,830 pound force times distance, which is 9.071. But now we have the weight of this beam. So if we're holding the beam stable here, the weight of the beam is going to be pushing it in a clockwise direction. And so we have the weight of the beam is 1,060 pounds, but the distance, well, we know the length of the beam is 21.7 feet long, but the entire weight of the beam isn't sitting at the right end. It's uniformly distributed, right? Uniform horizontal beam. So the weight is uniformly distributed. So that means its balancing point is in the middle. So half of the 21.7 feet. And so that balancing point is what we're going to use for the distance. And so our moment dealing with the weight of the beam would be 1,060 pounds times the distance would be half of the length of the beam. Okay. So that takes care of the clockwise direction. Now the counterclockwise direction, the only thing that's pushing it up is this R2. So we have R2 times, well, the distance from this point is 21.7 feet. We have this equation, and it's all numbers except for the variable R2, so we can solve for R2. Which would be 6,795.623 blah, blah, blah pounds. Okay, so now that we know R2, we can go back to the ups is equal to our downs. So the forces pushing the beam up would be R1 plus R2, which is 6,795 point blah, 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 is equal to our downs. Well, what's pushing this beam down is this 14,830 pound force, along with the weight of the beam, the 1,060. And so plug those in, plug in the 6,000 number for R2, and we get R1 is 9,160.78 and so on pounds. Please take a look at problem 4. It's a little different than the last couple problems because the weight changes, and so does the balancing point. That means we're going to have 2 equations, not just one, for the clockwise is equal to counterclockwise. But then if we have 2 equations with 2 variables, we know how to solve a system of equations. So there's my hint for problem 4. Take a look at it, see if you can draw the pictures, and then come on back and watch the next video.